Today we begin discussing sequences, and we will move right into series with the next video. And let me just say, when I took Calculus 2, which was the spring semester 1998, my freshman year of college, this material with sequences and series and convergence and divergence, this is when I fell in love with math. And this is when, to me personally, math started to seem like a puzzle or a game where you're trying to, you will see, right? It started to seem like a puzzle to me, which who doesn't like puzzles? And I kept taking math, and eventually, well, here I am. Okay, so I hope that you enjoy this material on sequences and the coming series as much as I do, as much as I did and continue to. So, first of all, what is a sequence? Well, a sequence is just an infinite list of numbers, say A1, A2, A3, A4. You can certainly have repetition, okay? And some notation here for a sequence. A lot of times you'll write an, say n equals 1 to infinity, or you might just see an, or you might see listed the elements a1, a2, a3, like this, okay? This is all notation for a sequence. Now, fundamental in our understanding of sequence is what the limit of a sequence, okay? So what is the limit of a sequence? Well, this is just like the notion of a limit at infinity of a function. In fact, I will connect it to that momentarily. So the idea, at least, well, limit as n goes to infinity of an equals L. This means that the sequence an gets closer and closer to L as n grows without bound. As n grows without bound. Well, this is the idea. Maybe I'll put a box around it, and then I will define a few other things. Okay, so definition, maybe I need to put it here. We say a sequence is convergent, or maybe I'll say converges, and converges to L, provided this limit L exists as a finite number, and then if L is infinity, well, I'll say infinite, which should include minus infinity. So if L is infinite, or the limit does not exist, then the sequence an is divergent or diverges. Maybe I will use the verb for both of these. The sequence diverges, and the adjective diverges. The adjective, as I was saying, is divergent. It's just like, so the notion of convergent, divergent being adjectives, converges, diverges being verbs. It's just like when we were discussing, say, improper intervals like this. Okay, now, well, how are we going to find limits of sequences? I guess that is a big question and quite an important one. So how do we find limits of sequences? I will do this in blue. Question. Of sequences Well, we can use, well, first of all, we've been calculating limits of functions at infinity since, say, Calc 1. Okay, so the answer, well, one answer, I will say, answer 1, is suppose f of x is a continuous function. Say this is continuous on 1 to infinity. And when you evaluate this function at integer values, you get the sequence an, right? Because an is not defined, sequence is not defined on the whole real line. It's just it's a list. So we only have a1, a2, a3, a4. Maybe you start at 5, and then you have a5, a6, a7, a8, goes to infinity. Okay. So suppose you have a continuous function such that an is the function evaluated at n. Well, then, if the limit, let's say as x goes to infinity of f of x equals L, we have the limit as n goes to infinity of an is L. So I will state it like this. This is fine. What this means is everything we know about limits of functions we can use when we think about sequences. In particular, what can we use? Number 1, we can use L'Hopital. Now, I will state, perhaps with L'Hopital, I will state it in terms of functions. Well, maybe I'll just verbally state L'Hopital's rule, and I'll do an example. What is L'Hopital's rule? How do we use it? Well, let's just state it in terms of going to infinity. If you are taking a limit as you go to infinity of a quotient, so this is something you need continuous function, or I should say differentiable function divided by differentiable function, okay? So this would be a quotient. And then let's suppose when you try to think about what's happening, you get plus or minus infinity over plus or minus infinity, or you get 0 over 0. L'Hopital's rule says you can take the derivative on the top, take the derivative on the bottom, reevaluate the limit. Okay? So we can use this for sequences, even though sequences like this are only defined on, say, positive integers, because of this correspondence. Okay, so number 1, we can use L'Hopital. The other one, this one I will state for sequences because it's a little easier to state in terms of sequences explicitly, is the Squeeze Theorem. Sometimes this is called pinching theorem. So let me state this for sequences because that's what we're working with, but it really comes from the corresponding statement for continuous functions. It says the following: if, let's say, an less than or equal to bn less than or equal to cn for all n. And, okay, so I have 3 sequences, and the limit as n goes to infinity of an equals the limit as n goes to infinity of cn is L, then the limit as n goes to infinity of bn equals, L. So you have these 2 sequences that are both converging to some number L, and you have this third one that's somehow trapped in between, that it must also converge to L. Okay, these are 2 things we can use. A third thing we can use is growth rates, which I will talk about momentarily, but before I do, let's do a few examples. Oh, well, there's a few more in particulars we can use. For example, if you have a continuous function, you can bring the limit inside, things like this, even though we're working with sequences, because of literally what I'm erasing right now, that if you have some function on 1 to infinity, and the limit as x goes to infinity is L, then the corresponding sequence where you just evaluate at the integers, or positive integers, I should say, has the same limit. Here are 4 examples of sequences. You may not be able to see them all at the moment. Here are 4 examples, and we will use what we know about functions on 1 to infinity and also the squeeze theorem, which I mentioned, to evaluate the limits of all of these sequences, and then we will discuss growth rates. Okay. Now, here and here, both of these are L'Hopital type problems. And I verbally mentioned L'Hopital, but let's do it in these examples. What do we see? Okay. In this one, the numerator and the denominator are both growing without bound. And so we get infinity over infinity. So if we want to calculate the limit as n goes to infinity of n plus 7 over e to the n, okay? If we think about, well, the corresponding continuous functions, we would be able to take the derivative on the top, take the derivative on the bottom, reevaluate the limit using L'Hopital. Let's do this here. Limit as n goes to infinity, and I can even write L'Hopital like this. Well, take the derivative on the top, take the derivative on the bottom, and now you see the bottom is, well, exponential. It's e to the n. This is growing without bound. We have a fixed numerator. This limit is 0. Okay? Similarly, in this problem, natural log grows without bound. It goes to the point 0, 1, goes like this. This would be, for example, y is ln x. Of course, putting in n plus 3 does not, it changes the graph, but doesn't change the behavior at infinity here. So this is growing without bound, growing without bound. We have infinity over infinity. We can take the derivative on the top, take the derivative on the bottom, reevaluate the limit. Okay, so if we want a limit as n goes to infinity of ln n plus 3 divided by n plus 1, we take the derivative on the top. It's 1 over n plus 3. We take the derivative on the bottom. Well, this is just 1 divided by 1, which is just this. Okay, and this is 0, again, because the denominator is growing without bound. So here we have 2 different, maybe I should do some examples that converge to something other than 0. Okay, coming. I just got the idea. But these 2 converge to 0. And we will see, in fact, 3 of the 4. These are all convergent. 3 of the 4 will converge to 0. Okay, well, now this one. These 2 are not L'Hopital, okay? Because, for example, this is just the natural log of something. And this, the numerator is not going to infinity. In fact, the numerator is not a differentiable function. It's just minus 1 to the n. It's bouncing back and forth. Oh, let me put my L'Hopital here. This I use L'Hopital. Okay. Now in this problem, I mentioned one thing we can use, well, all the tools of limits for continuous functions. The natural log is continuous, which means we can bring the limit inside. Okay, so if we want the limit as n goes to infinity of natural log tan inverse of n, well, this would be equal to the natural log of the limit n goes to infinity of the tan inverse of n. This, as we know, is pi over 2. So we get the natural log of pi over 2 here for this limit. This is the answer. Converges. All of these converge, 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 converge. Maybe I will do a few more. I was going to jump right into growth rates, but since everything here converges, we'll do a few more. Then we'll talk about growth rates. Okay, here, now, this one we have to think a little bit because let's draw a picture of this sequence. Let's pretend we didn't have the minus 1 to the n. Then it would be, I'll just do some tick marks. It would be like this. It would be going down to 0, right? This would be thinking about it as 1 over n squared. On the other hand, we could also think about negative would be here, going to 0. And what's happening with this actual sequence is it's bouncing back and forth. So first it's negative, then it's positive, then it's negative, positive, negative, positive, like this. You see this limit is 0. You see we're actually squeezing this. So you can argue this if you wanted to by saying that negative 1 over n squared is less than or equal to dn is less than or equal to 1 over n squared. And then this goes to 0, this goes to 0, and then Squeeze theorem will tell you that this goes to 0. In fact, we could see what's happening on the graph. Okay, here are 4 more, and you can see there's a relationship here, right? AN and CN. Then we take minus 1 to the n times each one. Okay, so these two are the continuous functions, or if you thought about them as functions f of x, and these things would not be, we have this minus 1 to the n times that. Okay, but these are really great exercises to think about. Now here, these two would have been things we thought about in Calc 1, for example. How could we calculate this limit? Well, you could use L'Hopital, but you certainly don't have to. You can just divide everything by the highest power that you see, which is n squared. So we have 1 plus 2 over n, 3 minus 7 over n squared. This is easier than L'Hopital because in this problem you'd have to use L'Hopital 2 times, and this one even more than that. So if I have polynomial divided by polynomial, I will never use L'Hopital. Okay, just divide by the highest power that you see. In this case it's n squared. And now this term goes to 0, this term goes to 0, and the limit here is 1/3. Let's do this one, Cn. And again, this one is very much like in Calc 1, for example, where we can divide by, let's say I'll divide by the highest power in the denominator. Although you have some choices here, I would get into the 8 over into the 4, which is into the 8 minus 4, minus 6 over into the 4, and then I have 1 minus 11 over into the 4. Okay, this term and this term, they both go to 0. The denominator is approaching 1, but the numerator is growing without bound. This limit is infinity or does not exist as a finite number. Okay, now let's jump to the other side. Okay, we saw in the last example of 4 where they all converged, we had a sequence that went to 0 and that was here, 1 over n squared, and when we multiplied by a minus 1 to the n, it went to 0. And it really was the Squeeze theorem, okay? But here it's very different because what's happening, well, we have calculated this, okay? So as you're getting very large, let's say here is 1/3 and here is negative 1/3. As n gets very large, this sequence is doing this. Okay? It's just bouncing back and forth between 1/3 and minus 1/3, or very close to, I should say. So this limit does not exist because it is oscillating like this. It goes back and forth as n is large between minus 1/3 and 1/3, bouncing back and forth. Now this one, well, similarly, this will not exist, but what's happening here, let's think about the picture, is you have here Cn, which, you know, if you take off the minus 1 to the n, that's this one, okay? this is going to infinity, but then we add the minus 1 to the n, and we are, I'm getting a little bit carried away. We are getting further and further away from 0, but alternating. So we are bouncing back and forth, further and further away from 0, okay? This one will not exist, the limit, okay? My picture is not very great. Because it's oscillating, it's not going to infinity. I think I need a little more space to write the word oscillating. It's not going to infinity or minus infinity. It is bouncing around positive, negative, but growing in absolute value. Okay, so these are very nice examples because we really need to think where we have to think about adding this minus 1 to the n part. And that was something that didn't really come up in Calc 1 because, for example, this function is, it doesn't correspond to like a continuous function on the real line. Okay, now, after seeing those number 8 examples, let us discuss growth rates, because this is something that you can use in this course, and it will make your life so much easier if you have this sort of understanding down. This is something I would like to discuss with you, which is quite important. At least it's something you can use with sequences. And this is the growth rates of functions. And so let's take k bigger than 1 for the moment to make this an exponential that's going to infinity. If you have, and I will talk about exponential functions momentarily, but if you have an exponential, let's make this comment now, okay? If you have an exponential function with base bigger than 1, it looks like this. Okay? If you have an exponential function with base less than 1, it looks like this. Well, this is with base 0 less than 1. I'm talking about here in the growth rates is really this picture where I have an exponential function that is going to infinity, okay? An exponential function that is going to 0 is certainly not growing faster than polynomial, and so I'm not considering it here. Okay, this here means grows significantly. If you read this to this, it says grows significantly slower than, like this. So this is about growth rates. And for polynomial, you can have k equals 1. That's just n, but here you need k bigger than 1. All 4 of these go to infinity as n grows without bound, but they do not go to infinity at the same rate. And this is this growth rates. So the log grows significantly slower than polynomial, grows significantly slower than exponential, and finally the thing that grows the fastest, factorials, okay? And I will remind you, if you, just as a recollection, n factorial is n times n minus 1, n minus 2 to 3, 2, and 1. You just multiply like this. And 0 factorial is defined to be 1, okay? It has to be, trust me, it has to be, so that, for example, counting formulas and all of this, they work the way they do, well, because 0 factorial is 1. Another thing, you could, for example, recursively define n factorial, and this will come up in the ratio test, but n factorial equals, well, it's n times, what do you see here? All of this. Well, n minus 1, n minus 2, etc. It's n minus 1 factorial. So this is n minus 1 factorial. So this gives you a way to think about n factorial in terms of n minus 1 factorial. And this one holds for n bigger than or equal to 1. This is only really defined for non-negative integers. Okay, this would say 1 factorial is 1 times 0 factorial, and that's definitely true. Okay, so this is the factorial function. I will put a box around this too. And this grows the fastest of them all, of these 4 that I have listed here. What we are looking at is a graph in Desmos that shows the growth rates of these 4 different types of functions that we just saw on the board. And the first one in blue here is the natural log, and I have kind of connected these integer value points, and I go through n is 30 with a dotted line, at least for the continuous ones, so that we can see it a little better. So we see here the natural log, and compared to the others, here I have k is 3. But I can vary that a little in my Desmos illustration. Compared to the others, which the green is polynomial, this would be x cubed. The black is exponential, this would be 3 to the x. And then the red dots are in factorial. Well, you see the log is very tiny, and then x cubed certainly grows grows slower, I should say. 3 to the x is very big, but the factorial is even bigger. It's sort of growing off the chart here, even at n equals 10, we can't see it on our graph, and we go up to maybe 70,000. Okay, well, this is a side comment. We can calculate this. What is 10 factorial? Okay, yeah, it's way off the charts. It looks like it's over 3.5 million, and I only go up to 70,000. Whereas, well, we have, if I did 3 to the 10, this is 59,000, and you see it approximately here. Well, 59,049, right? Less than 60,000. It's still on our graph. Now, if I change this, for example, I can change it to 4. You might think that because we see this black, which is now 4 to the x, it's bigger than this factorial for a few, right? Here, even n equals 7. 7 factorial, we see is less than 4 to the 7, but that's not going to last for very long, because once we get further out, and the growth rates I had on the board is really talking about this infinite tail. As n gets very large, what's happening between these functions? Okay, so we see here, and I have also built into this, we could have k equals 2. So now this is x squared, 2 to the x. And then, of course, we have the natural log, which has no k in it. And we have n factorial. But in all of these, well, this is supposed to be illustrating this growth rate that I had. We can see the factorial, n factorial grows faster than them all. Then comes the exponential. Okay, then polynomial, and finally the slowest growing is the logarithm, natural log. All 4 of these, though, go to infinity. Now that we have looked at the graph, how can we use this for sequences? Well, if you feel comfortable with this, which I hope you do, we can use this without having to use L'Hopital every time. For example, if you have a sequence that's a quotient and you see a factorial divided by a log, something on this side divided by something on this side, that will go to infinity. If you have an exponential over a polynomial, that will go to infinity. If you have a log over a polynomial, as we did over here, this will go to 0. And we had also, what do we have? Polynomial over exponential. This will go to 0. So if you go from this way to this way in a quotient, goes to infinity. If you go from this way to this way in a quotient, goes to 0. And you can use this without having to show your work for L'Hopital if you understand the growth rates, which I would definitely work to, right? Okay, let me erase. We will do a few more examples with sequences. Here are 4 more examples. Here. Now, let's use what we know about growth rates. You look at the numerator, what's growing the fastest? 5 to the n. This is what will dominate the numerator as n gets large. You look at the denominator, well, there's only one term, so the denominator will look like the natural log as n gets large. And then 5 to the n well, it's significantly bigger than the natural log of n, this means the limit as n goes to infinity of an is infinity or does not exist, like this. Similarly here, well, the numerator 10 to the n dominates. The denominator is one term in factorial. This is significantly smaller than in factorial, and so we may take a limit as n goes to infinity of bn. And what's in the numerator grows slower than the denominator by our growth rate discussion. We get 0, okay? Here, well, this is not a quotient, but again, we have 2 that are minus 1 to the n times something. It's always very important to think about things like this. This part is going to infinity here. Well, this is growing faster than this one, right? So 3 to the n minus n is going to infinity. And then we put this minus 1 to the n part. It is going to be it's this thing where it's getting further and further and further away from the 0, but it is that's an absolute value, but it's bouncing around, right? So the limit as n goes to infinity of Cn does not exist because it's oscillating. Okay? Finally here, well, if you ignore the minus 1 to the n, we have 1 over n factorial. N factorial that goes to infinity and goes to infinity very fast. So without the minus 1 to the n, this part, or you could say an absolute value, dn is going to 0. If you add the minus 1 to the n, it's still going to 0. That was this picture where it's going to be something like this, right? Maybe mine is not all going to 0. But the idea is you are doing this and then getting smaller and smaller and smaller, closer to 0 in your oscillation. We still get going to 0. So the limit as n goes to infinity of dn is 0. And you noticed, even for instance, this one, I didn't use a L'Hopital, I used our knowledge of growth rate. This one, technically, I could not use L'Hopital because this n factorial is not a continuous function defined on the real line, but I used our knowledge of the growth rates. So our challenging one, I have n, 8 to the n over 3 to the 2n plus 1. Okay, I was looking at my notes. Okay, this is probably so far, at least in my opinion, the most complicated one we have seen. Because if you try to think about growth rates, we have exponential in the numerator, well, times n, and then we have exponential in the denominator, but it's not obvious what's going on, right? Maybe it's going to infinity, maybe not. We don't necessarily know. Looking at it, it can stump one or someone, okay? Well, let's do some algebra here to try to see the right power or the right base for the exponential, because here we see a 3 to the 2n plus 1. So let's do some algebra, then we will be able to see what's happening. We have n. And then here, if I pull out a 3, I'll leave the numerator alone. If I pull out a 3, I have a 3 to the 2n, okay? And then, this is n over 3. We still have 8 to the n. And then this, well, one of the properties of exponentials, oh, my black is back here, pardon me, is that if you have this is what we see to the BC. This is a to the B to the C. So here I have 3 to the 2n. This will be 3 squared to the n, okay? So this is 3 squared to the n. And now I have n over 3 times 8 over 9 to the n. Okay, well, it still might not be obvious, because if we even go back to thinking about, and this does define a continuous function on the real line. If we go back to try to think about L'Hopital, this first thing is going to infinity and this is going to 0. It's exponential with base less than 1. But we can rewrite this, and you might remember doing this sum from Calc 1. This would be 9 over 8 to the n. Now I have it written as something going to infinity over something going to infinity, like this, where you can think about using L'Hopital because I'm in the right form. But I'm not going to use L'Hopital. I'm going to use our knowledge of growth rates. But you see, I have it as written as function divided by function. My function in the numerator is polynomial. My function in the denominator is exponential. And if you remember these four, it's exponential with base bigger than 1. Okay, so we have that n grows significantly slower than, or I could even say n over 3, that's fine, than 9 over 8 to the n, because this is exponential with base bigger than 1. Therefore, the limit as n goes to infinity of an is 0, like this, because what's in the numerator is growing slower than what's in the denominator. If you wanted to use L'Hopital on this, you certainly could, but you can also use growth rates. Let's discuss the limit of an, which is 1 plus 1 over n to the n. When I have done, let's say, classes where we're really in class and not online, and I just ask my students what they think this limit might be. Well, some of them have seen it, but they don't know why the limit is what it is. And then the ones that haven't seen it, they guess 1. And one reason I like to do this one is because it's an important caution, right? This is function of n, function of n. If I had, for example, this is going to be a side comment, if I had this and I wanted a limit as n goes to infinity, well, of course, f of x is x squared is continuous. You can bring the limit inside. This would be this. And here you take a limit, 1 over n goes to 0. We get 1 squared, which is 1, okay? And perhaps your intuition is saying you could do the same thing here. Just bring the limit inside. But you cannot do this because this is a function of n. Here it's not, so I can bring the limit inside. And if I had n to the 5th or n to the 6th, or I should say to the 5th, to the 6th, where my outside function was x to the 5th or x to the 6th, then I could bring the limit inside, no problem. Here you cannot. And this example, while it's quite beautiful, is also a caution about if you have function all to the n, as we will see some with series, you cannot bring the limit inside because this is varying with n, this is varying with n. And I will say the limit of this is not 1, okay? That's what most people guess. The limit exists, it is absolutely not 1. So let's see what the limit is right now. Okay, I enjoy this. Now, as I mentioned, it's difficult to calculate a limit when you have something all to the n. But what can we do to get rid of an exponent like this? Well, log properties. Let's consider yn, which is the natural log of an. Okay, then what is yn? Well, let's just take the natural log. This is 1 plus 1 over n to the n. Okay, it might look like I've made this more difficult, except properties of log says if you have a power on the inside, you can bring it out in front. So this is n, natural log. Okay, so what I'd like to do is figure out a limit as n goes to infinity of yn. Well, let's think about what's happening here. This is going to infinity, right? This second term here is going to the natural log of 1, which is 0. We cannot use L'Hopital if we have infinity times 0. We have to have 0 over 0 or plus or minus infinity over plus or minus infinity. But we can rewrite this as follows. We can rewrite this as ln 1 plus 1 over n divided by 1 over n. And now this is something we could use L'Hopital on, for example. Because the numerator is going to ln of 1, 0. The denominator is going to 0. Okay, now, just to make this easier on myself when I use L'Hopital, let me just let's say, I need another letter. Let's say P equal 1 over n. And then, as n goes to infinity, we know P goes to 0. And I can rewrite this in terms of P. This is ln 1 plus P over P. Okay, this just makes my L'Hopital easier. You don't have to do it like this per se, but it's just going to make my life a little bit easier. Now let's evaluate, well, the limit as n goes to infinity of yn. This is a limit as I have simplified P goes to 0, ln 1 plus P over P. Okay, now we will use L'Hopital. We take the derivative of the top, take the derivative of the bottom. Limit as P goes to 0. Take the derivative on the top, take the derivative on the bottom. Well, divided by 1. And this is 1. Okay? Without a doubt, the limit of yn is 1. Now, I'm not finished. Okay? Therefore, the limit as n goes to infinity of an. This is where we use the fact that if you have a continuous function, you bring the limit inside. The limit as n goes to infinity of, well, an is, if yn is the log, an is e to the, right? Because these are the log and the exponent are inverse functions. If we have this relationship and we want to solve for an, raise both sides e to the, and you will see an is e to the yn, like this. Now this limit, well look, we calculated this, is what I was saying. You have a continuous function, which y is e to the x, a continuous function, bring the limit inside. We have e to the 1. Okay? Yes! Okay. This is how cool this is. So this sequence, what have we just shown? This sequence here, we have just shown the limit as n goes to infinity of an is e. This is what I was saying. It sort of defies your intuition because you might just glance at it and think it's going to 1. It's going to e, okay? I really like this example. So maybe I will put a box around this. This is what we showed with this little trick of considering the sequence where we take the log of an, like this. Okay. I would like to do one more thing in this video, and the main reason I'm doing this, well, not only is it good for us to think about in terms of the sequence, but this discussion will come up when we're doing geometric series, which I think is the very next video that you will see. And I will just mention that we already did it, and so this is important for us, okay? What happens if you take, so here r is a number, it can be positive, negative. Well, if it's 0, this is trivial, it's just 0, the whole sequence. But we're taking r to the n, and we're trying to figure out what happens as n goes to infinity. Now, some things we know. Let's graph. We're going to have a bunch of cases here. If we have a number, if this is actually an exponential function, we know what happens. And I've already graphed this, but it's quite important. I will graph again. So if you have a base between 0 and 1, this is the exponential function. If you have a base bigger than 1. This is the exponential function, okay? But then, this is really, r is bigger than 1. These are the exponential functions. But there's more r's than just that. So first of all, let's just write these down. This limit we have, okay, if, so this is 0. In fact, I can do this because if r equals 0 is the 0 sequence, and then here is infinity. So far, so good. Now, if r is literally equal to 1, the sequence is 1 for all n. 1 to any power is 1. Okay, so now we have treated what you're probably most comfortable with, which is all the non-negative numbers, r. Now, we really just needed to treat negative r, which, if you think about it, let's say I had a minus 1/3 to the n, right? Let's just think about this, and then we can make the statement sort of fill out our chart. This is a minus 1 to the n times 1/3 to the n, r to the n. If r is less than 0, like this. Okay? Minus 1 to the n times absolute value of r to the n, where we have thought about what happens with positive r. Okay, so if you think about a case kind of like this, where in absolute value you are here, I meant between 0 and 1. Well, then the absolute value is going to 0, and this will bounce around, something like this, and get closer and closer to 0, squeeze theorem, that kind of thing we have talked about. So if you have an r where, like this, then this would be the graph of, and your actual series is bouncing around, but still getting closer and closer to 0. So this part here, I can change to just say, okay, if you have a minus 1 to the n, this d and e, as it oscillates, minus 1 to the n literally looks like this. Between 1 and minus 1, bounces back and forth, 1 and minus 1. Okay? Oh, close my parentheses. Now similarly, let's go back to if you're negative now, say like r is minus 5. So example, r is minus 5. You want a minus 5 to the n. Well, the absolute value is in a picture like this. And this would be here, a graph of like this. But what is this actual sequence doing? It is bouncing back and forth and getting further and further away from 0, because in absolute value you're going to infinity. Okay, we saw some examples like this, but you are bouncing back and forth, oscillating. Okay, so this is still the case. If you have absolute value bigger than 1, but you are negative, so I can change this here to not just say if r is minus 1, it would be here, r less than or equal to, because we already had equals. So now let me draw a number line and see if I have everything. Now, in practice, if you are given a sequence, you don't have to be this abstract. You would have a sequence with a very specific r. My r is minus 2. Oh, okay. But I'm doing this now because in the next video, when we get into geometric series, there will be a moment when I evaluate a limit of something like this. So what have we treated? Let me draw a number line, make sure we have all of the cases. Okay, so absolute value of r, here's minus 1, here's 1. This is my number line for r. Absolute value of r less than 1 is in here, this sequence goes to 0. Okay, we have treated that. If r equals 1, that's here. I've covered this. The limit is 1. The limit is 0. Minus 1. This place, the limit does not exist. D and E. And then out here, if r is less than 1, the limit, D and E, oscillates. Up here, bigger than 1, the limit is infinity. And that's the reason at D and E. Okay, yeah, we have treated every case. So this is what happens with this sequence r to the n. And as I mentioned, I'll use this in our next video.